Let's work with some inverse trig functions. We want to find y, where first of all, y is the arc sine of 1/2. You can read this to yourself or interpret this as meaning y is the angle whose sine is 1/2. And remember, the arc sine function's range is negative pi over 2 to pi over 2. So the answer we give for y has to be an angle in this range. One way to think of this is to think that I'm looking for y such that the sine of y is positive 1/2. And if you look at the range, this involves quadrant 4 and quadrant 1. So I'm looking for an angle in quadrant 1 whose sine is 1/2. That angle is the angle pi over 6. Well, let's continue and look at another example. Here we want to find y, where y is equal to inverse sine of negative 1, and this is another notation that can be used instead of arc sine. Again, you need to pay attention to the range of the inverse sine function. It is negative pi over 2 to pi over 2. And we can interpret this as I'm looking for an angle such that the sine of that angle is the number negative 1. Since that's negative, and the answer, or the value of y, has to be between negative pi over 2 and pi over 2, which is quadrant 4 and quadrant 1, we need to give an angle that fits this situation in quadrant 4. And actually, the result is the angle negative pi over 2. Let's look at another example. Here I want to find y, where y is the angle whose sine is negative 2. Now let's interpret this as the sine of y is negative 2. There is no angle whose sine is negative 2, so there is no solution or no value of y that satisfies this equation. Well, each of the problems we worked can be worked using a graphing calculator. So let's take our calculator and see how we might have worked those same problems. What we want to do is go into y equals and graph the inverse sine function. Now we have to graph the inverse sine of x even though it had different values in there. If I look at a window, a good window to use is negative 1 to 1 in the x direction. Recall that the inverse sine doesn't exist, or its domain is negative 1 to 1. I've put in a scale of 1/4. And then the y min and y max that I've used are actually the range. It's negative pi over 2 to pi over 2. So let's take a look at that graph. And this is a graph of the entire inverse sine function. Its entire domain is negative 1 to 1. Now, one of the things that we found just a minute ago was the inverse sine of the number 1/2. So let's put in an x value of 1/2. And what we see is that at the bottom of the screen, y is 0.5235 and so forth. That number is exactly pi over 6, and you can check that out on your own. The other angle we found was found by finding the inverse sine of the number negative 1. And if you find that, you'll see that that comes out to negative 1.57, which is exactly negative pi over 2. Let's work with the inverse cosine function. We want to find y, where y is arc cosine of 1. Arc cosine is the inverse cosine function. The first thing to do is to think that the range of the inverse cosine or arc cosine is 0 to pi. So any value for y that we find or give must be between 0 and pi. Now interpret this as meaning I want the cosine of some angle to be 1, and I'd like to know what that angle is, and that angle has to be between 0 and pi. The cosine of 0 is exactly the number 1, so y must be 0. Let's try another. Again, we want to find y, where y is inverse cosine of negative square root 2 over 2. First thing to do is to think of the range of the inverse cosine function as being 0 to pi, and interpret the statement as meaning the cosine of some angle is negative square root 2 over 2, and I need to know what angle that is. Since this is negative, and the range or the interval from 0 to pi involves quadrant 1 and quadrant 2, our answer must be some angle in quadrant 2 whose cosine is negative square root 2 over 2. in radians, that angle's 3 pi over 4, and that's the value of y we're looking for. Let's look at these on a calculator. What we want to do with our calculator is we want to go into y equals, and we want to enter the inverse cosine of x and take a look at a graph. Now, as a window, I've set the domain, which is -1 to 1 in the x values, and 0 to pi, recognize 3.14, and so forth here, as my range value, as my y values. I'm going to take a look at the graph, and here's a graph of the entire inverse cosine function. It only exists between -1 and 1. To check the work that I did, I'm going to go to Calc and choose the option called Value. And the first value I want to put in for x in my inverse cosine function is the number 1. When I push Enter, it tells me that when x is 1 in the inverse cosine function, y is 0, which confirms what I found. The second problem that I worked, using value again, said put negative the square root of 2 divided by 2 in for x in the inverse cosine function. When I push Enter, I get a decimal, 2.356, and so forth. If you check that out, you'll find that that's exactly 3 pi divided by 4. Let's work with some inverse trig functions. We want to find the degree measure of theta, where theta is the arctangent of 1, or the angle whose tangent is 1. Now, looking at the arctangent function, its range, in degrees this time, because we want a degree measure, is -90 degrees to 90 degrees, not including either -90 or 90. So we're looking for the angle whose tangent is 1. In other words, the tangent of some angle comes out to 1, and the angle needs to be between -90 and 90. Now this is quadrant 4 and quadrant 1, so our answer has to be in quadrant 1. And the angle in quadrant 1, whose tangent is 90, is the angle 45 degrees. Let's try another. Again, we want to work with degrees. We want to find the degree measure of theta, where theta is the inverse secant of 2. Now the range in degrees of the secant, of the inverse secant, I should say, is 0 degrees to 180 degrees. And so I'm looking for an angle whose, let's say this, whose secant is 2, or the secant of some angle is positive 2. 0 to 180 is quadrant 1 and quadrant 2. The secant is negative in quadrant 2. So we want to find an angle in quadrant 1 whose secant is 2. The angle that we're looking for is 60 degrees, and there's a couple of ways to get to 60 degrees. You could think this through and think if the secant of some angle is 2, then the cosine of that angle must be 1/2, since they are reciprocals, and it might be more comfortable to get to 60 degrees using this relationship. Let's work with some inverse trig functions. We want to find y in radians if y is equal to the inverse cosecant of -3. Well, if we have the inverse cosecant, we can find the inverse sine of the reciprocal of -3. And I'd like to do this one with the help of a calculator in radians. So let's go to our calculator. And on our calculator, we're going to do the inverse sine of -1 divided by 3. And we get -0.3398. And that's the value that we were looking for. Let's try another. This time we want to be in degrees. And we're going to use a calculator to help find theta in degrees if theta is equal to the arc cotangent of -0.3541. Now, arc cotangent is the same as the inverse cotangent, and there isn't an inverse cotangent button on the calculator. So what we're going to do is find the inverse tangent, and that's using the notation that you'll see on your calculator, but it's the same as the arc tangent of -1 divided by 0.3541. So now let's do that on our calculator. But the first thing we need to do is set our mode to degree mode, because we were asked to make this calculation in degrees. And then we're going to find the inverse tangent of -1 divided by 0.3541. And we end up with -70.5 degrees. Now that's not an angle that's in quadrant 2. So I need to take that, add 180 to it. I'm going to take negative 70.5 as the value that I found for this inverse tangent in degrees, and add 180. So probably to be correct, I should add 180 right here to indicate that that's what I need to do. When I add those together, I end up with theta as approximately, because I did round the 70.5, 109.5 degrees. Let's work with some inverse trig functions. We want to evaluate the expression without using a calculator, the sine of the angle whose tangent is 3 over 2. Now the range of the arctangent, the inverse tangent function, is from negative pi over 2 to pi over 2. This is positive. Between negative pi over 2 and pi over 2 is quadrant 4 and quadrant 1. But since that's positive, we need to think about some angle in quadrant 1. And this is the angle whose tangent is 3 over 2. And since tangent is opposite over adjacent, I'm looking at some angle here whose tangent is 3 over 2 as labeled. Now using the Pythagorean theorem, the hypotenuse of this triangle, if that's a right angle right there, is the square root of 9 plus 4, which is the square root of 13. Now what I'm interested in finding is the sine of this angle, whose tangent is 3 over 2. The sine is opposite over hypotenuse. So the sine of the angle whose tangent is 3 over 2 is the opposite side over the hypotenuse, or 3 over square root 13. If I rationalize the denominator here, I end up with 3 square roots of 13 over 13 as a result. Let's do another example like that. We want to evaluate, without using a calculator, the tangent of the inverse cosine of negative 5/13. Now if you look at the inverse cosine, its range is from 0 to pi, which is quadrant 1 and quadrant 2. The cosine's positive in quadrant 1, but this is a negative value. So we're looking for this to be some angle in quadrant 2. So I'm going to draw an angle with its terminal side in quadrant 2 and label so that its cosine is negative 5 over 13, attaching the negative to the 5 because I am to the left of the y-axis, so in the negative x direction. Well, this is one of those special right triangles that I recognize the opposite side must have value 12, and you could solve for that using the Pythagorean theorem. But what I really want to find now is the tangent of this angle whose cosine is negative 5/13. And so I want the tangent of the angle that I've drawn. Tangent is opposite over adjacent, and so in this case that's 12 over negative 5, or negative 12/5. Let's work with some inverse trig functions. We want to evaluate, without using a calculator, the cosine of the arctangent of square root 3 plus the arcsine of 1/3. The arctangent of the square root of 3 is an angle, and so is the arcsine of 1/3. So I want to find the cosine of an angle plus an angle. I'm going to use a cosine sum identity, and let me start by writing that identity down. The cosine of a plus b is cosine a cosine b minus sine a sine b. Now if I match that with what I'm trying to find, a is the arctangent of square root 3, and b is the arcsine of 1/3. So to find the cosine of a plus b, I need to find the cosine of the arctangent of the square root of 3 times the cosine of the arcsine of 1/3, all of that minus the sine of the arctangent of the square root of 3 times the sine of the arcsine of 1/3. And so we'll need to continue from there. What we need to find are the cosine of the arctangent of square root 3, the value for that. We need to find the sine of the arctangent of square root 3, a value for that. We need to find the cosine of the arcsine of 1/3, and we need to find the sine of the arcsine of 1/3. And I want values for each of these. I'm going to draw a couple of pictures. Now, the arctangent of square root 3, that's positive, and the inverse tangent's positive in quadrant 1. And I want the opposite side to be square root 3, the adjacent side 1, so the hypotenuse must be 2. And so the cosine of that angle, this angle right here, is the adjacent side over the hypotenuse, which is 1/2. The sine of the angle I just drew is the opposite side over the hypotenuse, which is square root 3 over 2. And now we're looking at our next two values. I need to sketch a picture of the angle whose sine is 1/3, again in quadrant 1, but this time I want the sine of my angle, so opposite over hypotenuse, to be 1/3, which makes the adjacent side, and you could work this out with the Pythagorean theorem, would be the square root of 8, which is 2 square roots of 2. What I'm interested in finding is the cosine of that angle, which is the adjacent side over the hypotenuse. So that's going to be 2 square roots of 2 over 3. And then the sine of that same angle is going to be the opposite side over the hypotenuse. So continuing, we need to take those values and put them into our expression, and here it is. We're looking for the cosine of the arctan square root 3 plus the arcsine of 1/3. Using the cosine sum identity, we found it's equal to this. And now I'm going to fill in the values that we just determined. And you could look back at them on your own if you need to. The cosine of arctan square root 3 is 1/2. The cosine of arcsine of 1/3 is 2 square roots of 2 over 3. I have that minus. I'm at this point. The sine of the arctan of square root 3 is square root 3 over 2. The sine of the arcsine of 1/3 is 1/3, and I need to figure this out, or simplify, really. It comes out to 2 square roots of 2 over 6 minus the square root 3 over 6. And combining those fractions, that's 2 square roots of 2 minus the square root of 3 all over 6. Okay, let's look at part B for the same example. We want to evaluate, without using a calculator, the tangent of 2 times the angle whose sine is 2/5. Well, this is a tangent double angle question. Recall the tangent double angle identity is 2 tan B over 1 minus tan squared B, where B is the angle. In this case, arcsine of 2/5 is B, the angle whose sine is 2/5. Now that's positive, so I'm going to sketch an angle B in quadrant 1 and label sides so that the opposite over the hypotenuse is 2 over 5. Now using the Pythagorean theorem, this side comes out square root 21, and what I'm going to need to use is the tangent of that angle, which will be the opposite over the adjacent. So I'm ready to fill values into this identity to come up with 2 times the tangent of B, which is 2 over the square root of 21, over 1 minus the tangent of B, all squared. And all I got to do is simplify. Let's do a little bit of simplifying. This is 4 over the square root of 21, all over 1 minus 4 over 21. And we want to continue to simplify, but let's move to another sheet. What we have is 4 over the square root of 21 over 1 minus 4 over 21. To simplify, I can clear the fractions within the fraction, or let me do this. Let me rationalize the numerator alone by itself, and that'll be 4 square roots of 21 over 21. And then for 1, use 21 over 21 and subtract 4 from that to get 17 over 21. Then if I multiply by the reciprocal of the denominator, 21 over 17, I'll have 4 square roots of 21 over 21 times 21 over 17, and the 21s will simplify. I'll end up with 4 square roots of 21 over 17, and that's the value I was looking for. Let's work an example involving inverse trig functions. We want to write the trigonometric expression as an algebraic expression in u, and what we have is the sine of the angle whose tangent is u. So I'm going to sketch an angle in quadrant 1 just to use as a guideline and call it u. Actually call it some angle theta, it's not u itself, and set things up so that the tangent of theta is u. So make the side opposite u and adjacent 1. Then using the Pythagorean theorem, the hypotenuse will be the square root of u squared plus 1. Now there could be an alternate picture in quadrant 4, since I don't know whether u is positive or negative. So we'll deal with the fact that u could be positive or u could be negative when we're finished simplifying. What I'm interested in finding is the sine of this same angle. Now the sine of this angle is the opposite side over the hypotenuse. The sine then is u over the square root of u squared plus 1. If I rationalize the denominator, I multiply the numerator and denominator by this radical, and I end up with u square roots of u squared plus 1 over u squared plus 1. And I'll just make a note, it could be positive or negative depending on the sine of u, since there's a u right here. Well, let's try another example similar to this one. We want to write the trigonometric expression as an algebraic expression in u. And this time we have cosine of 2 times the angle whose sine is u. This is a cosine double angle situation. But again, I want to draw a picture of some angle. I'll call it theta for the moment. I want to set up theta, and theta is this part right here, so that the sine of theta is u. Now the sine is the opposite side over the hypotenuse, and then using the Pythagorean theorem, the adjacent side's the square root of 1 minus u squared. Applying the cosine double angle identity, first of all, the cosine of twice some angle might be 1 minus twice the sine squared, or the sine, let's say, the sine of that angle squared, and we can simplify from that. Remember, cosine twice an angle is 1 minus twice the sine of that angle squared. Simplifying this, putting in what I know, I'm looking for 2 times the sine of, well, I should put in a value, but since I started not to, we'll rewrite one more time. I should put in the sine of the angle whose sine is u, and the sine of my angle theta is u. And so I end up with 1 minus 2 times u squared as my result. Now, considering whether u could be positive or u could be negative, since I'm going to square it, either way, this would be the result. Let's work an application problem. The optimal angle of elevation theta a shot putter should aim for to throw the greatest distance depends on the velocity v of the throw and the initial height h of the shot. Continuing, one model for theta that achieves this greatest distance is theta equals the arc sine of the square root of v squared over 2v squared plus 64h. Now, suppose a shot putter can consistently throw the steel ball with h equals 6.6 feet and v equal 42 feet per second. At what angle should he throw the ball to maximize the distance? Well, what we want to do is put 6.6 for h and 42 for v and find the arc sine of that result. So here's our model. Let's fill in the values we're going to use. we got arc sine of the square root of 42 squared over 2 times 42 squared plus 64 times 6.6. Well, this is definitely a problem where it'd be more convenient to make a calculation with a calculator. So let's go to our calculator and calculate that value. The first thing I want to do is check my mode and see that I'm in degree mode, and that'll work well for this problem. Now what I'm going to do is find the arc sine of the square root of, first of all, 42 squared, then divided by parentheses 2 times 42 squared plus 64 times 6.6, close parentheses for the denominator, close parentheses for the radical, close parentheses for the sine, arc sine, and I end up with 41.9, which leads to an answer of 42 degrees for the shot putter.